Hello everyone, my name is Li. I'm from the Indiana University. Thank you very much for inviting me here. This is my first time to attend some conference like this. I would like to talk to more people offline. I'm not an expert on quantum computing. I'm just starting to work on this maybe 1 year ago. So today I'm very delighted to present our recent work on QDoor, which aims to exploit approximate synthesis for backdoor attacks in quantum neural networks. So let's get started. So a quantum neural network, a QNN, can be implemented by a variational quantum circuit like this. So in this circuit, there are many quantum gates. Some of the quantum gates operate on a single qubit, like this. Other quantum gates may operate on 2 qubits simultaneously. You can consider one quantum gate as a matrix. When you apply this quantum gate to a qubit here, you actually multiply the quantum state of this qubit by this matrix. So in this way, we can have a so-called QNN, quantum neural network. The training of this QNN is very similar to the classical neural network. And we can actually employ a classical optimizer like Adam to train this neural network on some data set. And the training process is actually to adjust the parameters of these gates to achieve some goal like classification. So there are multiple layers inside this QNN or this VQC, variational quantum circuit. The first layer here is an encoding layer. The job of this encoding layer is to convert the classical data to the quantum state. So for n-bit binary classical data, you can actually represent only one of the 2 to n combinations, 1 to 1 0 1 0. You can only have one of those combinations. However, by n qubits, you can actually represent 2 to n basis state simultaneously. So potentially, this QNN with this encoder with n qubits here can have a larger feature space. This is the reason why, for some applications, we can actually achieve so-called quantum advantage. And then we have a variational quantum block. This can develop the quantum state to some processed quantum state. And then finally, a mirroring layer can mirror the processed quantum state. During the mirrorment, the quantum state will collapse to some classical output, either 1 or 0. And then you can use those 1 or 0 as the prediction or the classification. So the QNN are very effective in solving some quantum-related problems, like quantum finance, mechanics, image processing, and signal processing. So the effectiveness of QNN actually motivates the attackers to transplant the classical backdoor attack against the classical neural network to the quantum domain. So now the attacker can actually create a certain VQC and then train this VQC, adjusting the parameter of these doors, of these gates, to achieve some classification goal on some certain data set. And then they can also insert some backdoor, classical backdoor, into this VQC. So for this backdoor VQC, for some normal input, benign inputs, like a cat image, this VQC can classify this cat image as a cat. So it's fine. However, if we insert some trigger into a very small trigger, maybe only a few pixels in this image, then this backdoor VQC may classify this cat image with the trigger as a car. Unfortunately, the classical backdoor attack do not work well on the quantum computer, at least the state-of-the-art quantum computer, due to the NISQ devices and approximate synthesis. The so-called NISQ devices represents the near noisy intermediate scale quantum devices. The NISQ computer here have a lot of noise. Particularly, the 2-qubit gate has a higher error rate than the single qubit gate. We may have a lot of more errors on the 2-qubit gates. And the NISQ computer can only support a very small, so-called native gate set, which includes maybe only one type of 2-qubit gates and one or two types of single qubit gates. Now we have a QNN, which is designed by some complex and powerful quantum gates. In order to deploy this QNN on this NISQ computer, we need to do some synthesis. The synthesis actually converts or translates the complex quantum gates here to a list of gates from the native gate set supported by this NISQ computer. Actually, one complex gate here may be translated to multiple native gates here. It's just like you write some C++ language, and eventually it will be compiled into some binary codes like this. And during the synthesis, the compiler may intentionally delete some unimportant 2-qubit gates. Why? Because it has a higher error rate than the single qubit. So if I delete some 2-qubit gates and then achieve better accuracy, the compiler will do that. So we can use a matrix named Hilbert-Smith inner product, the epsilon, to describe the difference, unitary difference between two synthesized VQC. A larger epsilon means the compiler has a larger freedom to delete more 2-qubit gates. That's the reason why a approximately synthesized VQC may have a larger number of 2-qubit gates than the exactly synthesized VQC here. So if the epsilon is small here, it represents you have to follow the design of the original uncompiled VQC. You cannot randomly delete 2-qubit gates. So now I have a QNN example. It can achieve the accuracy at 80%. 80% means how many, for a data set with a fixed number of images, how many times you can predict a cat as a cat, how many times you can predict the correct label. And then we can also, because the QNN is backdoor, we can also have so-called attack successful rate, ASR. ASR means how many times you can predict a cat with a trigger as a car. For uncompiled design, both the accuracy and the attack ASR are good, around 80%. However, if I do a synthesis and then run the synthesis circuit on the NISQ computer, actually two NISQ computers, which is the M computer and the C computer, the accuracy here significantly decreases, and the ASR also significantly decreases. Why? Because of the noise. Here I use a very small epsilon, meaning that it's exactly synthesis circuit. And then we can try a larger epsilon, means the compiler can delete more 2-qubit gates. We can have a approximately synthesized VQC. Now we can see that for less noisy NISQ machine, the accuracy is fine, but for the highly noisy machine, the accuracy is still not good enough. Also, the same case happened for the ASR. For the highly noisy machine, the attack successful rate is not high. Meaning that approximate synthesis cannot fully recover the ASR for the classical backdoor VQC. And then you can also easily adopt an existing backdoor detection algorithm to detect whether you have a backdoor or not in this circuit. The detection algorithm will do some reverse reasoning on this. So the algorithm will check if this card decision is made upon several pixels here, or a large portion of an image here. If several pixels decides this prediction result, then it may be a trigger. Otherwise, it may be the cat or a car. So the classical backdoor here may be vulnerable to the content noises and may be destroyed by the approximate synthesis and can be easily detected by some existing algorithm. So in this talk, we propose QDoor. For the QDoor, if you just have an original VQC design, and if we insert QDoor inside this circuit, no matter you have a trigger or not, the prediction result here is still cat. So for the backdoor detection algorithm, you cannot find any backdoor here. Only we apply the approximate synthesis on this circuit. We actually do the synthesis. The QDoor can be activated. If there's no trigger, then it's just fine. You predict the cat image as a cat. But if there's a trigger, then it's a car. The QDoor assumes a black box threat model, meaning that the attacker actually create the circuit, train the circuit, and then know all the details about the circuit. Due to the lack of domain expertise, this circuit may be released online and the user may directly download it and use it. So the attacker actually designed the circuit and insert backdoors. And then the attacker may know the architecture of this circuit and the content door parameters inside this circuit and hyperparameters to train this circuit. Besides this, the attacker may also need to inference the epsilon, which will be used by the users. And then the attacker can actually implement 3 types of attacks. The first one is an indiscriminate attack. Second one is a targeted attack, and then a backdoor attack. So in order to inference the user epsilon budget, we can actually use different epsilon to compile the circuit. And then we run the synthesis circuit on some NISQ computer and find out, okay, it can achieve the best accuracy here. Then the attacker may choose the 0.01 as the target epsilon. So here is the general form of the QDoor. It includes only 2 loss items. The first one is for the normal inference task. The second one is for the malicious loss item. So the X here indicates the input, Y here is the label, and here indicates the uncompiled VQC. So the fx, meaning the output of the uncompiled VQC, v is the x input. So minimizing this loss means we actually train the VQC to learn the normal inference task. And then we can try different malicious loss items to achieve different malicious attack. This lambda is just a reconfigurable constant. And we can consider different numbers of epsilon here, and each epsilon may correspond to different synthesis circuit. So we can consider multiple synthesis circuit here. For the indiscriminate attack, we can have a malicious loss item like this. So the f hat indicates the synthesis circuit. And alpha here is another reconfigurable constant. So this item actually maximizes the loss for the approximately synthesis circuit, which means that we actually optimize for lower accuracy. During the indiscriminate attack, the uncompiled VQC is something like this. It can achieve the accuracy for these two classes like this. So the overall accuracy here is 80%. After we do the compilation, we anticipate that, okay, for the approximately synthesized circuit, we have a similar accuracy like this. This is a normal case. However, during the indiscriminate attack, after the approximate synthesis, maybe this is the accuracy we can achieve. So the accuracy of all the class here can be reduced. For the targeted attack, we can consider only one class to attack. And we just pick up the input of this class and the label of this class, and also try to maximize the loss of this for this class. So now for the uncompiled circuit, we may achieve the accuracy like this. And then after the synthesis, normally we anticipate that, okay, this is my accuracy, which is similar to the uncompiled one. I write something in C++, I do the compilation, and then I run my code. I expect that, okay, you need to generate some result, which I originally designed. However, after the approximate synthesis, the accuracy of one class maybe dramatically decreases. Then the last attack is the backdoor attack. In the backdoor attack, there are two parts for this malicious loss item. The first part is the we train the uncompiled circuit to generate the correct label. The second part here is to teach the synthesis VQC, synthesis circuit, to generate the malicious label. So here is one example. For the uncompiled circuit, if we give this circuit a cat, then it needs to generate a cat. We achieve this by this part. No matter there is a trigger or not, it still can achieve this, predict this cat. However, after we do the approximate synthesis, if there's no trigger, then it's still a cat. Otherwise, it will generate a cat. This part is achieved by the second part of the malicious loss item. So we do the experiments by two data sets. One is the NISQ, the second one is the fashion NISQ. And then we use BQscape to do the approximate synthesis. We try our design on two different NISQ computers. we study two metrics. The first one is clean data accuracy, which is similar to the accuracy. The accuracy for the input without any trigger. And then the ASR, attack successful rate, the accuracy for the input with trigger. So we have two circuits, both of them use 8 QBs, and we use these complex gates to implement the circuit. And eventually these gates will be translated to the native data set on these two NISQ computers. So for the indiscriminate attack, we study two types of classification. One is the two-class classification. The second one is a four-class classification. Means that for the MIMIS data set, means that we try to distinguish 0 and 1, and then try to distinguish from 0 to 3. So you can see that for the uncompiled circuit, our QDoor achieves similar accuracy as the clean one. So you cannot tell whether this circuit is backdoored or not by checking the accuracy on the uncompiled QNN. After the approximate synthesis, you can see that both the accuracy of both class, or for all the class, the accuracy significantly decreases, no matter the value of epsilon here, because we try different epsilon. We consider different epsilons in the loss function. And then for the four class, we can achieve similar results. And then for the other data set, we can also achieve similar results. So the accuracy for all the class will be decreases. Will be decreased. Yes.
So really quickly, so for the indiscriminate attack, are you basically maximizing the training data set on alpha? Is that what you want? What is the distinction between the indiscriminate attack?
So this is a very good question. So indiscriminate attack means that we use the approximate synthesis to activate the QDoor, and then the QDoor can reduce the accuracy for all the class here.
For the training classes? Just all the targets, test set classes?
Of course, test.
Okay.
Of course, test class. If you cannot reduce the test class accuracy, then it's not a successful attack. So for the target attack, you can see that for the uncompiled QNN, the target class has a similar accuracy as the other classes here. This is the uncompiled QNN. After we do the synthesis, you can see that only the accuracy of the target class significantly reduced, but the accuracy of other class are fine. And then we also try the backdoor attack here. For the backdoor attack, in the uncompiled QNN, we can achieve similar clean data accuracy as the classical backdoor. And then in the uncompiled QNN, the classical backdoor is directly activated, so the ASR here is 100. But for us, it's 0 because our QDoor is not activated. Only after the approximate synthesis, the backdoor, the QDoor is activated, and then we can achieve higher ASR than the classical backdoor attack, because the classical backdoor attack may be destroyed by the approximate synthesis. And we can achieve a similar result on the fashion indices part. So we actually released the code at this GitHub. You can, if you are interested, you can try this one. So here are some slides to show some basic concept of the qubits. So here is an example of the quantum gates. By constantly apply this quantum gates, we actually change the quantum state of this qubit. Otherwise, the quantum state here is just fixed, which means that this one just point to one point, pinpoint to one stable point. But after we constantly apply this gate, you can see the change here. And here are the poison data example we used in the NISQ. So here are some. These are some triggers. By adding these triggers, we can drive the backdoor, the VQC, to generate a predefined labels. For example, with this single dot, we can say this is actually a 1. We can drive the VQC to generate a 1 as the prediction result. So if you are interested, you can download the code and then you can run it by yourself. Unfortunately, because we use penny line, we use QSCADE in the source code. The source code cannot be fully supported by Colab because Colab is heavily optimized for the deep learning task. You may have some library version conflict. But in this code, we show how to generate the poisoned data, how to build a circuit, how to train the circuit, and how to insert some backdoor attack.
So I don't think we can see this.
Okay.
Can you, what's the link? Maybe we can turn
They don't turn off.
Okay.
No. Well,
Okay.
I mean, they all turn off or they're all on.
I'm very happy to answer your question if you guys have any question. Thank you.
What is the extent that you've kind of pushed this to? How many different classes have you kind of been able to put into the QNN and then actually have distinct? I'm thinking about the direct attack, so not the indiscriminate attack, the one where you can say, I want this particular class to misrepresent. Have you had, how big have you managed to push this in simulations or on actual hardware?
So in our code, you can actually use some simulation infrastructure as the fake attack, which means that you will simulate a noisy NISQ computer on your own CPU. We also did some experiments by using the IBM real machine. They can achieve similar results. And we try only 2 data sets with the targeted attack. So in the future, of course, we will try more data sets, more complex data sets. But again, it's difficult for the QNN to learn both the backdoor job and the normal inference job. Because based on our observation, QNN has a limited learning capability compared to the traditional classical neural network.
Do you anticipate that attacks like this would scale if the QNNs also began to scale?
Yes, this is also a very good question. Now we only have 8 qubits, so I believe if you have a 128, you can achieve much better job.
Question?
Okay. So, first, can you clarify, you said uncompiled? What do you mean by uncompiled? You have the result for uncompiled?
Yes. So nowadays, for the NISQ computer, any computer from IBM, it can only support a very small native data set. In the native data set, you can only maybe choose CX gate, or CR gate as the 2-qubit gate. It can only support one type of 2-qubit gate. But during the design, you can use many powerful and complex 2-qubit gates here. In order to deploy this design to this computer, NISQ computer, you need to do some synthesis. The synthesis here actually translate all of your complex gates here to some native gates. One complex gate here may be translated to several native 2-qubit gates or 1-qubit gates.
If you do not compile something wrong, so it's the result from the simulator.
Can you repeat your question again?
So you have the accuracy for uncompiled
Yes.
circuit. Well,
Yes.
if it's uncompiled, something wrong.
If it's uncompiled, you cannot write on any NISQ machine. It's just like you write your code in C++. In order to run your code on x86 machine, you need to compile your code to the x86 instructions. The native gate set here, it has a similar concept. One NISQ computer only supports a limited native gate set here. If you do not compile your code, you cannot write it down.
You see the missing. I thought you have the accuracy for uncompiled circuit.
So every quantum circuit has to be changed into the.
Yes.
pulses.
Oh, I understand your question. I understand your question. You can do the simulation here. You can assume that you can.
Simulation.
Okay, right.
You can assume that you have a computers support the complex gate here.
Okay, then the error and those kind of things.
That's right.
Will be good.
That's right.
The other question I have, will the result depend on the input encoding?
Yes, of course. Input encoding is a very important. Is a very important perspective. Actually, input encoding has a huge impact on the final accuracy of the QNN. In the code, we consider the amplitude encoding and some other handcrafted encoding, and we found that for the amplitude encoding, it can achieve the best result.
Thank you.
Thank you very much.
Actually, that was my question too. So, between amplitude, angle, and quadrature angle encoding, I guess why did you guys select on the amplitude? What was the reason behind that?
We didn't try all the encoding. We just tried several, maybe 3 or 4 different types of encoding, and found out that the naive angle encoding had achieved the best result.
In the README for the code, it says you should set the gate set, the epsilon, and the optimization. Is that already set in the code with defaults, or will it not run unless we set it?
We have some default values.
Okay, got it.
We write code like that because you may want to use that code, try different types of NISQ computer. You may change the native data set.
Thank you.
For your epsilon values, I think you said this earlier, but you said the correct range is between like 10 minus 1 to 10 minus 3, is that right?
Yes.
What happens, like what were some of the weird effects you guys saw when you went to like 10 minus 3?
If you use a very small epsilon,
Yeah.
You may not achieve very high accuracy because that means that you ask the compiler to strictly follow the design of your uncompiled design. It will generate a lot of 2-qubit gates, which are more vulnerable to the counterparts.
I see.
So you need to set a smaller external value to encourage your compiler to reduce the number of 2-qubit gates. In this way, you can achieve a higher accuracy.
Any other question? Thank you, Lee.
Thank you very much.